Hey, Harsh here. If you have ever built a database, you know the single most crucial decision you face is determining its structure. Do you optimize for speed or do you optimize for data integrity? Today, we are diving deep into two opposing forces of database design: normalization, the path to database integrity, covering everything from fundamental 1NF to all the way to rare 5NF, and denormalization, the intentional introduction of redundancy designed to make your applications speedy. Normalization is foundational to relational database theory, tracing back to EF Cord in 1970. The core philosophy is simple: store every unique piece of information exactly once. Think of it as an accountant of a giant corporation. You wouldn't want to store the company's tax ID number on every single invoice, purchase order, and employee record. If that ID changes, you face an update anomaly requiring hundreds of manual, error prone changes. The objective of normalization is to achieve standardized data format across your entire system. This reorganization makes the database easier to maintain and modify. If you fail to normalize, you risk the inconsistency and redundancy problems. The solution lies in applying the normal forms, a cumulative set of rules, meaning you must satisfy the first form before moving to the second, and so on. We begin with the most fundamental rule that establishes very structure of a relation, the first normal form. Before diving deep into these forms, we need to first understand what functional dependency is. If you know the student ID, you can find the student's name. So the student ID functionally determines student's name. Now, 1NF is the simplest rule, is the baseline requirement. If your table has comma separated values in a column like math, comma, science, comma, music, or repeating attributes like contact 1, comma, contact 2, comma, contact 3, you have violated 1NF. This is non-atomic structure which makes queries difficult and error prone, as finding all customers who have bought a mouse will require complex string parsing. The fix is simple but effective. You eliminate repeating groups by putting them into separate rows or new entities altogether. In our e-commerce example, a customer buying two items gets two separate rows, each linking the customer ID to a single product. This simple step lays the groundwork for all subsequent normalization efforts. Here is where it gets interesting: the second normal form, or 2NF. 2NF specifically addresses redundancy issues that still exist even after achieving 1NF, particularly when you have a composite primary key. Imagine our orders table has a composite key consisting of order ID and a customer ID. If we also store the customer ID repeatedly next to every order that customer places, the customer name only depends on the customer ID, which is part of the key. This is a partial dependency and it leads to a massive redundancy. To comply with 2NF, you must separate customer information into its own table keyed by the customer ID. The original orders table now holds the foreign key, which is customer ID. This successfully eliminates the redundancy of customer details, simplifying updates and ensuring data maintenance is much cleaner. If 2NF cleans up dependencies on parts of keys, 3NF cleans dependencies between non-key attributes themselves. This is called transitive dependency, often phrased as a non-prime attribute that cannot depend on another non-prime attribute. Think of it as like this. In a table storing employee details, if you have employee ID determining department ID, determining department name, then department name is transitively dependent on employee ID through department ID. This violates 3NF, as changing the department name requires updating every employee record in that department. To achieve 3NF, we extract the dependent non-key attributes into a new table. In our example, we create a suppliers table keyed by supplier ID and a products table keyed by product ID. The original table only retains the product ID and links to the supplier ID via the products table. This decomposition improves data integrity and reduces duplication significantly. For most practical applications, achieving 3NF is often considered sufficient. Boycott normal form, sometimes called 3.5NF, is the gold standard for integrity in relational design. While 3NF is usually sufficient, BCNF plugs the few remaining holes primarily when dealing with complex dependencies or composite keys. The rule is succinct. Every determinant must be a candidate key. A determinant is the attribute or set of attributes on the left side of the functional dependency. If A non-key attribute determines a prime attribute, BCNF is violated. Let's look at a university example. Course determines instructor. Since course alone does not uniquely identify a row in the original combined table, the composite key, student ID, course is not a super key and BCNF is violated. To fix this, we create two tables. The course instructors table is keyed by course, making the dependency valid because the determinant is now a primary key. This greatly reduces redundancy as the instructor name for a new course is now stored only once, not repeating for every enrolled student. The fourth normal form addresses multi-value dependencies. This occurs when a single record contains multiple unrelated facts. For instance, storing a publication's keywords as a multi-valued attribute violates 4NF. The fix is to separate multi-valued attributes like keywords into its own table, creating many-to-many relationship. This ensures each row captures only a single unique relationship. The fifth normal form, 5NF, is truly academic for most systems, dealing with rare join dependency. Essentially, 5NF ensures that joining smaller, non-redundant table doesn't introduce new information that wasn't already available, minimizing the risk of redundancy from the complex joins. Unless you are designing a highly integrated, highly stable schema where data decomposition is critical, stopping at BCNF is almost always the right decision. The key insight here is normalization prioritizes data integrity and write performance. For transactional systems, those dealing with many updates, deletes, and inserts, OLTP, normalization is a clear winner. It ensures that customers' address changes, you update it once the customer is stable and all the records remain consistent. This is crucial for systems like banking, inventory management, or CRM. However, normalizing data breaks into many smaller, narrower tables. This is the cost of integrity. When you need to retrieve comprehensive information, say customer's name, address, and all the order details, you need to perform multiple potentially expensive join operations. When data volume increases, these join operations can significantly degrade query performance. This performance hit is exactly why you need denormalization. Once you have normalized your tables to achieve 3NF or BCNF, you may find that the performance suffers, especially if you have complex queries joining many large tables. Here's where reality hits: denormalization. It's a controlled, deliberate step backward. You are intentionally adding redundancy to execute queries quickly. Why? Because historically, join operations have been expensive and slow, especially at scale. Think of it as compiling a comprehensive report. In a full normalized system, getting a sales report requires joining the customers, orders, and product tables every single time. In a denormalized system, you might pre-join or duplicate the customer and product names directly into the orders table. Now generating the report is single fast table scan. While this increases the risk of inconsistency and requires more storage, it gives you the speed needed for real-time application and dashboards. Denormalization isn't just about throwing structure away, it's about applying strategic redundancy. One of the simplest methods is introducing a redundant column. If you frequently join the customer table just to get customer's name, why not copy that name directly into the orders table? This instantly removes the join cost. A slight update complexity later saves a massive query time now. Similarly, table splitting is a performance hack. If your table has millions of rows, you can use horizontal splitting to break it by region, say separating US customers from European customers. Queries focused on US only hit the smaller US table, dramatically improving query performance. Vertically splitting is great if you have very wide tables. If hospital's patient table contains common details like name, ID, and are rarely accessed like medical history, split them. Queries accessing just the patient name and ID don't have to scan the massive medical history text field, making the reads much faster. Materialized views and mirror tables represent an advanced but critical denormalization strategy. If you have a complex calculation, say calculating the lifetime value of every customer, that takes 30 seconds to run and your application needs this value frequently, you use a materialized view. You run that 30-second query once, store the result in a view, and then your application gets the answer instantly until the view is refreshed. Mirror tables are often used for mission critical report generation. Organizations generating these sales reports and or user statistics often need to scan massive datasets. Instead of running these huge queries on the master, normalized OLTP database, they use a replicated mirrored copy optimized purely for reading. The main trade off here is synchronicity. Maintaining multiple copies of data and keeping them in sync can be costly, and data inconsistencies can arise if your replication fails. You must choose if slightly stale data is acceptable in exchange for guaranteed speed. Normalization gives us integrity, denormalization gives us speed. The slide encapsulates the strategic reversal of priorities. The primary draw of denormalization is the drastic improvement in query response time. When you eliminate joins, reads are inherently faster, which improve the overall user experience and application scalability, especially under high load. Furthermore, flattening the data model makes queries much simpler, reduce the complexity of writing maintainable SQL. However, you must accept the drawbacks. Denormalization is a commitment to redundancy, which inherently increases storage usage and risk of data inconsistency. If an employee changes their name and the name is copied across 10 different denormalized tables or columns, you must ensure that all 10 tables are updated. If even one fails and your data drift, this makes updates and inserts costlier and increases overall maintenance complexity. Which strategy is right for your project? The answer hinges on your primary use case. Use normalization where data integrity is paramount. This is the standard for online transaction processing OLTP systems, such as operational database for e-commerce platform, where customer data, order details, and inventory must be perfectly consistent after every transaction. Normalization ensures strong referential integrity. Use denormalization when fast read performance is critical. This is a standard practice in online analytic processing OLAP systems, data warehouses, and BI tools. For example, a monthly sales report requires scanning historical data quickly. A denormalized summary table provides instant access without needing to join billions of rows. You tolerate a risk of anomaly because the data changes infrequently and speed outweighs update efficiency. For most modern organizations, the choice isn't either or, it's both and. You establish a highly normalized database for your core operational data, guaranteeing transactional integrity. This is the source of truth. You then create a secondary denormalized structure specifically optimized for different downstream consumers. For example, your analytic team might use a dedicated denormalized data warehouse layer, OLAP, or your application might use a cache denormalized views to serve fastest responses to users. This hybrid approach allows you to achieve both maximum data integrity in transactional layer and maximum speed in analytical layer. Even as new technologies like NoSQL and big data platforms offer favor flexible denormalized schemas, understanding the principles of normalization is crucial for consistency and modeling relationships at the design level. The goal is an effective design that strikes a balance. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.